Okay, we'll get started with the second part of the exam review. So this is our penultimate class session for this course. So we'll be back on Monday to finish things off. First thing, maybe you may be curious about how the exam went. You probably know your own results, but just as a whole, this midterm 3 had an average of 11.8 out of 20, which was almost identical to the second midterm. So we had very similar results, which is typically what we see for this course, so nothing surprising there. And then the final exam coming up, usually the percentages are it's similar to these two, so you can kind of have that in your mind, but try to surprise me and do better, that'd be great. All right, so that's a quick rundown of the results. If you have questions about where you currently stand in the course regarding your grade, please come see me before the final and we can square that away. It's pretty simple to calculate the grade on our grading scale, but if you have any problems or just want to verify, please let me know. Okay, so we're going to move on to start talking about the rest of these problems. We're going to go through about 11 today. All right, so the next one is about formal charges and Lewis structures. So, is this the version that you guys have? I had two versions of this. Yes, okay, good. For the Lewis structure of chlorite that obeys the octet rule, what is the formal charge on the central atom? All right, so the first thing we have to do is draw the Lewis structure, and the key word here is obeys the octet rule. So if you have a problem that tells you, asks you something about the octet rule or says obey the octet rule, or, that means we have no more than 8 electrons around any of the atoms. Now we know that there are some atoms that can violate the octet rule, but here we're going to try to draw a structure that completely obeys the octet rule, even if it might be possible to go beyond that. So let's go through the steps for drawing a Lewis structure. So we have to know the formula of the ion that we're talking about. So chlorite is ClO2 minus. So review the polyatomics if you've forgotten any of them. So then we have to count electrons. And just remember, the number of valence electrons comes from the position on the periodic table. So we have chlorine and 2 oxygens. Chlorine is here in group 7, so it has 7 valence electrons. Oxygen is in group 6, so each oxygen contributes 6. All right, so we have a chlorine. There's one of those with 7 electrons. And then for oxygen, we have 2 of them, ClO2 minus. Each one has 6 electrons. And then remember, when we have overall charges, we have to account for those. So this one has a negative charge, which means we have to add 1 extra electron to the fray. So we get a total of 20 electrons for this ion here. So when we go to draw the Lewis structure, we know we can only use 20 total electrons. And we put the least electronegative atom in the center, which is chlorine. We start with single bonds to the 2 oxygens. Okay, so that's completing the octet of the oxygens. Remember that we start by drawing 8 electrons around each outer atom. So each oxygen now has a single bond and 6 non-bonding electrons for a total of 8. And then when we've done that, we still have 4 electrons left over because this is 16 of our electrons. We have 20 total. So then any additional ones go in the central atom. Okay? All right, so that's going to be the structure that we get. Now let's evaluate the octet rule, see if we need to draw any double bonds. So each oxygen has 8 electrons, and our central atom now also has 8 electrons. Remember, octet rule counts shared electrons as a pair as well, so you have 2, 4, 6, 8 electrons surrounding the central chlorine atom. So this structure obeys the octet rule. We could potentially draw some double bonds here, but we don't want to go past the octet rule, so we stop here, and now we're going to evaluate formal charges. So we want the formal charge on the central chlorine atom. So for the chlorine, remember that for formal charge, we start with the number of valence electrons that it has as a free atom, which is 7. That's the number of electrons that it contributed up here. We subtract the number of bonds, so this is valence electrons. We subtract the number of bonds it has, which is 2. It has 2 single bonds. This is the total number of bonds. And then we subtract the number of non-bonding electrons. So this has 1, 2, 3, 4 electrons around the central atom as non-bonding electrons. So we have to subtract 4 from that. This is non-bonding. And so in that we get a +1 formal charge on this chlorine. All right, so that's going to be choice C. This is not the best Lewis structure for this compound because we have a +1 formal charge and we have minus formal charges on the outside, so we could cancel those out by drawing a double bond. But if we want to follow the octet rule, obey the octet rule, we can't draw any more bonds, and so we're left with a +1 formal charge. Any questions on that? Okay, let's move on to number 14 then. All right, this one deals with nomenclature. Select the best name for Al2S3. So when we're doing nomenclature, the first thing we need to think about is what kind of compound it is. Is it an ionic compound or a covalent compound? Because those have slightly different rules. All right, so if we think about the compound, so what kind of element is aluminum? Is it a metal or a nonmetal? Okay, we talked about this last time. Aluminum is a metal. It's not the most obvious metal, but it is on the left side of the P block. It's a main group metal. Sulfur is, of course, a nonmetal because it's on the right side. So going back to the periodic table here for a second. We have aluminum, which is right here. It's on the left side of the staircase, so it's a metal. Sulfur over here, clearly a nonmetal. Okay, both in the same row. All right, so we have a metal combined with a nonmetal, which means it's an ionic compound. And the key point about ionic compounds compared to covalent compounds is that for ionic compounds, we don't use any prefixes. All right, so we only use prefixes for covalent compounds. So we just name the cation, which is aluminum, without changing it. And then the anion, sulfide, with an IDE ending. So we put this IDE ending on the anion. Really, for any name, whether it's covalent or ionic, we put an IDE ending on the second element, but in this case it just goes on the sulfur, sulfide. So you just do cation plus anion with IDE ending. So it's just aluminum sulfide. So that would be choice E here. Okay, so a lot of these have prefixes, so A and B both have prefixes, which we don't use in ionic compounds. Choice C doesn't have the correct ending on the sulfur. And for choice D, remember that we only put Roman numerals in parentheses for transition metals. So for metals that have variable charges. Aluminum is a main group metal, so it doesn't get a charge in parentheses. Although it wouldn't be terribly wrong to do that. We never put charges or anything on the nonmetal, just on the metal if it's there at all. Okay, questions about nomenclature? Yeah. So for the D block, we're not really going to have you memorize which charges each element forms. Just be aware that if you're in the D block, it's necessary, especially for the ones in the middle, to have the charge in parentheses when you name it. We're not going to ask you which ions does iron form, because in reality it's a lot. I mean, 2+ and 3+ are the most common, but transition metals often can form, ions that go from +1 all the way to their highest valence, which would be +6 or something for iron. So there's a huge range, and that's something we're going to ask you about directly. Just be able to recognize when you get the formula of a compound how to determine what that charge is, and then how to incorporate that into the name of the compound. There are a few D block metals that are invariant, so zinc is always +2, so we don't usually put the 2 in parentheses, and silver is pretty much always +1. There's a couple like that you don't usually use in parentheses, but we're not going to hold that against you if you do. Anything in the D block, when you name it, if you put the little number in parentheses, that's fine with us. And that's the only time we'll use those is for transition metals. Anything else? All right. Number 15. Now we're talking about molecular structure. So which of the following molecules are linear? All right, so we notice that each of these formulas has only 3 atoms in it, 1 of something and 2 of something else. So there's only 2 possibilities. It's either linear or bent when you have 3 atoms. Those are the only possibilities. And so whether it's linear or bent is going to be determined by whether the central atom has lone pairs or not. And there's different numbers of lone pairs on the central atom can give rise to different structures. So if we start with CO2, we count electrons. We get 4 for carbon, 2 for 2 oxygens with 6 each. So we have a total of 16 electrons in CO2. And we've drawn this Lewis structure millions of times before. So CO2 has 2 double bonds, no lone pairs on the central atom. AX2. And remember that this is going to be linear. If we just have two things on the central atom, they want to go 180 degrees apart. So anything with AX2 without any lone pairs is going to end up linear. But then for the rest of these, if we do water, we've done water a lot before too. When we draw the Lewis structure for water, we can't have anything but single bonds because it's hydrogen. And we still have two extra pairs to put on the central atom. So this one is AX2E2, and this is one of the bent geometries. There's two AXE notations that give rise to a bent. There's AX2E2 as well as AX2E, which is one lone pair. So either of those would give a bent geometry with different angles, but they're nonlinear. Okay, so if we're looking for the linear ones, this one's linear, this one's not. If we go to xenon difluoride, this is sort of a weird one. It's a compound of a noble gas, which do exist in rare circumstances. This is one of them. We have 8 valence electrons from xenon. It's a noble gas. We have 2 fluorines with 7. So this compound is going to have 22 valence electrons. So when we put all the valence electrons in here, we get 2 bonds to fluorine. We complete the octets of the fluorines. We still have 6 more electrons to put on the central atom. Alright, so this is AX2E3. And this is maybe not the most obvious geometry, but if we think about AX2E3, there's a total of 5 electron groups, so they go into a trigonal bipyramidal arrangement. There's 2 X's and 3 lone pairs, that's a total of 5. And remember that the lone pairs in the trigonal bipyramidal electron group arrangement always go in the triangular part. So our 3 lone pairs go around the equator. That leaves us with fluorines up here and here in a linear geometry. Alright, so this one is an example of linear. And it's the only example, I think, of an AXE notation where you have lone pairs on the central atom and it stays linear. Alright, and then finally for SO2, we have 6 electrons from sulfur, 6 each from oxygen. So this one's going to have 18 valence electrons. When we draw them around, we get 16 of those completing the octet for oxygen. That leaves 2 more on the central atom. The best Lewis structure for sulfur dioxide is going to have 1 or 2 double bonds, but it doesn't matter whether we draw those in or not. The geometry is AX2E, which is bent. Alright, so that one's also bent. So 1 and 3 are the linear ones here. Now as a quick rundown, there are obviously a lot more geometries than linear and bent, but as a quick rundown of these types of formulas that have a central atom and 2 outer atoms, you have a few possibilities. You have AX2, which is linear, AX2E and AX2E2 are both bent, and then the last one, AX2E3, is linear. All right, so as I said, the number of lone pairs on the central atom is going to determine whether it's linear or bent. But there's a lot of other geometries that go beyond this, so take some time to review that as well. Questions on this or VSEPR in general? All right, hopefully this is all coming back. Okay, number 16. Which of the following has the greatest dipole moment? Okay, so we're talking about polarity here. Anytime we see the word dipole moment, and anything that has a dipole moment is considered polar. So if we're looking for the greatest dipole moment, we're looking for most polar. Okay, so for the polarity of molecules that we're talking about here, we need to think about both the polarity of the bonds themselves as well as the geometry. It comes down to both things. All right, so we have, again, there's a table in the notes that I gave you back then that summarizes all of the different geometries and whether they're polar or not. So if we start with CCl4, when we draw the Lewis structure of this, we get just carbon with 4 chlorines around it, no lone pairs in the central atom. Carbon very rarely has lone pairs. All right, so this one is AX4, and remember that all of the geometries that are AX whatever with no lone pairs, AX2, AX3, AX4, AX5, AX6, if there's no lone pairs in the central atom and all of the X's are the same like they are here, they're all chlorines, those are all nonpolar. Okay? So AX anything is nonpolar as long as there's, again, no lone pairs in the central atom, as long as all the outer atoms are the same like they are here. Okay, so that one's nonpolar. If we go to PF5, phosphorus with 5 chlorines. And again, for this one, once we complete the octets of the outer atoms, we're out of electrons. This one is now AX5 instead of AX4, which again is nonpolar because there's no lone pairs on the central atom. Okay, so I'm not drawing the full geometry necessarily. All right, if we go to xenon tetrafluoride, we did xenon difluoride last time. I guess we skipped one, O2. All right, O2 we don't even have to consider. It's definitely going to be nonpolar. If we have diatomic molecules, that's a molecule that only has 2 atoms in it. If the 2 atoms are the same, it's nonpolar. If the 2 atoms are different, it's polar. We have 2 oxygens, so it's going to be nonpolar. We don't have to even think about it beyond that. All right, and then for xenon tetrafluoride, which is choice D, when we draw this one, we get our fluorines on single bonded. We complete their octet. And we still have 4 more electrons to put in the central atoms. This one has an AX4E2. And this one has lone pairs, so we do need to think about the shape a little bit. So for AX4E2, there's 6 electron groups, so they go into an octahedron, which is also called a square bipyramid. So the xenon in the center, and remember for any structures with lone pairs, we're going to put the lone pairs as far apart as possible. So for AX4E2, we arrange them 180 degrees apart, which leaves the fluorines out here. And this one is square planar and nonpolar, okay, because we have the bond dipoles for between xenon and fluorine are going to cancel out in both directions. All right, so this is not the most obvious nonpolar geometry because it has 2 lone pairs, but this is another example. So again, we have a dipole that goes this way that cancels out with that dipole, and the same thing in the other direction. All right, so in other words, if we have a dipole that goes in the positive x direction, we also have one in the negative x that cancels, positive y, negative y, depending on how we define our coordinates. So no net polarity in this molecule, so it's nonpolar as well. So finally, all of these are nonpolar, so they don't have any dipole moment. So the last one, which is NF3, which should be our winner here, if all the rest of these are correct. When we draw NF3, draw that again. So we have room. For NF3, we're left with 1 lone pair on the central atom, AX3E. And no matter what the x's are, if you have 1 lone pair on the central atom, for any geometry, it's going to be polar. So that's another one that we don't have to think too hard about. Anything with 1 lone pairs on the central atom is polar. So we circle that one because that's the only one that's polar at all. So it's going to have the greatest dipole moment. Usually for more complicated molecules, we're not going to have you rank them in terms of dipole moment. If we ask for the one that has the greatest dipole moment, look for the one that's polar. If we ask for one that has the smallest dipole moment, look for the one that's nonpolar. And I would say it's very rare that we would have you rank polarities for molecules. We'll have you rank polarities for individual bonds. That comes from the electronegativity difference. But for molecules, it's a little bit harder to do because it depends on both the electronegativity difference and the geometry, and it's not always an easy comparison. But here it's an easy comparison because only one of them is polar at all. Okay? Any questions on that? All right, so we're seeing that there's a lot of problems. We have at least one more here that deal with drawing Lewis structures. So if you need to refresh that, that's going to be very important because it will come up on several problems on the exam, even if the problem is not about Lewis structures. If it's anything related to polarity, hybridization, geometry, all of those things require Lewis structures. So you want to make sure you're able to do those quickly and efficiently. All right, so the last one here that deals with Lewis structures is acetic acid, CH3OOH. So we want to figure out how many sigma bonds are there, and then enter the answer as a numerical answer. All right, so the concept here is that when we have bonds, in the valence bond theory where we're using overlap of atomic orbitals and hybrid orbitals to form bonds, we have either single bonds and we have multiple bonds, and those are going to have different combinations of sigma and pi. So sigma bonds are the ones that are sort of a head-to-head overlap. Pi bonds are the ones that are side-to-side overlap between 2p orbitals. So you have 2 different kinds of bonds that occur in molecules. Anytime we have a single bond, in the valence bond approach, we assume that it's a sigma bond. If we have a double bond, it's always going to be one sigma and the rest are pi. So double bond is two total bonds, so there's one sigma and one pi. And then for a triple bond, which is the highest that will go for main group molecules, you have one sigma and then again the rest are pi, so that leaves two pi bonds. So when we're counting bonds, whether they're sigma and pi, we just need to know whether it's a single, double, or triple bond, and that'll tell us what types of each bond are in that. So for this one, we have to draw the Lewis structure of CH3COOH, including all the lone pairs. So the structure for this, we have a CH3. So when we give formulas like this, hydrogens that come directly after carbon are bonded to the carbon that comes right before it. So CH3 means that the first carbon has 3 hydrogens bonded to it, and then it's going to be bonded to the carbon next to it. And then something that might not be obvious from the formula, but we should learn, is that COOH means you have sort of this arrangement here. You have carbon bonded to one oxygen and carbon also bonded to an O, which is also bonded to an H. So whenever you see that in acetic acid, COOH, that's what that group looks like. Okay, so we want to make sure that we're familiar with that. Okay, so now we have to fill in any double or triple bonds. And so the shortcut we can take for these kinds of compounds is that all these atoms are, well, it's hydrogen, carbon, oxygen. So those things, except for hydrogen, want to have a complete octet. So to complete the octet, carbon wants to have 4 bonds and 0 lone pairs. So I've introduced this shortcut before, and it's very helpful for drawing some of these structures quickly. If you have a nitrogen in your structure, it's going to tend to have 3 bonds with 1 lone pair. So all of these are a total of 8 valence electrons, just different combinations of bonds and lone pairs. Oxygen, 2 of each. And then, of course, for hydrogen, like I said, if you do anything besides this, I will die a slow death if you put anything besides just 1 bond of hydrogen. Okay, so just 1 bond on hydrogen. Please don't try anything else. All right, so, and no lone pairs, of course. All right, so we have to fill the rest of these in. This first carbon here has 4 bonds already, 1, 2, 3, 4, so we can't add any more bonds to this carbon. This carbon here, it looks like it has only 3 bonds, 1, 2, 3, and then this oxygen only has 1. So if we make a double bond between carbon and oxygen, that will give this carbon its 4th bond, it will give this oxygen its 2nd bond, and then this oxygen also wants to have 2 lone pairs, so we'll put those in as well. This oxygen here also already has 2 bonds, but it needs 2 lone pairs to complete its octet. Alright, so if we follow these rules, we can usually pretty quickly determine where there's going to be double or triple bonds in the structure. This one only has 1 double bond, the rest are all single bonds. So if we label the bonds and figure out how many sigmas and pi's there are, each single bond is a sigma. And then each double bond is going to be 1 sigma and 1 pi. So that double bond there is a sigma and a pi. Okay, so if we count the sigmas, 1, 2, 3, 4, 5, 6, 7, we have a total of 7 sigma bonds and 1 pi, which this doesn't directly ask about, but is also there. All right, questions on sigma and pi bonding or other aspects of valence bond theory? Okay, let's move on then to number 18. All right, so for number 18, we're using molecular orbital theory to predict bond order. All right, so we did pretty well on this on the last exam, but there's it is a bit of a complicated topic. But remember, the idea here for molecular orbital theory is we think about what kind of valence orbitals we have. Carbon is in the p block, so we're going to be using s and p valence orbitals. And then we have to arrange the molecular orbitals in order from lowest energy to highest energy and fill them with the correct number of electrons. So remember that when we do this, we have 2 orbitals that are derived from the s orbitals. Whenever 2 orbitals overlap, you get a bonding and an anti-bonding. So the s orbital that's on each carbon, the 2s orbital, overlaps to form a sigma 2s, which is our lowest one, and then a sigma star 2s, which is the next one. We go into the p orbitals now. When p orbitals overlap, they're going to form sigma and pi molecular orbitals. So the ordering of those differs a little bit. So if we're for boron, carbon, and nitrogen, when we go to the p part of the diagram, for the p orbitals, we have first a pi set of orbitals. So pi orbitals are always doubly degenerate, 2 orbitals at the same energy. Then we get a sigma, So the bonding orbitals come first, and then the highest energy are going to be the anti-bonding orbitals that are derived from the p orbitals, pi star, and then sigma star. All right, so that's the ordering of the molecular orbitals for anything with boron, carbon, or nitrogen in it. So there's a total of 8 atomic orbitals. There's a 2s orbital. There's 3 2p orbitals from each atom. 8 orbitals overlap to form 8 molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8. Now the other difference is for oxygen, fluorine, and neon, or anything in those same columns as we go to the second half of the p block. The 2s orbitals come in the same order, sigma and sigma star. But then we get a switch in the p part where the sigma 2p comes first and then the pi. So the bonding orbitals in the p area of the diagram switch. Pi star and sigma star stay the same. Alright, so it is important for certain problems, especially if you're dealing with unpaired electrons, to remember the ordering of these 2 orbitals here especially. That's the only part that switches between the 2 diagrams. But we need to remember the order of these, and then once we know which one we're using, again, we're talking about carbon here, so we're going to use this diagram here. We populate it with the correct number of electrons. So for C2, 2-, we have each carbon has 4 valence electrons. It's in the the group 4 of the periodic table. We have 2 more for the 2 negative charges, so you're going to have a total of 10 electrons here. So C2, 2- is going to have 10 electrons, and we fill them in this diagram from the lowest to the highest until we run out of electrons. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we follow the same rules for filling orbitals that we use for atoms. We go lowest to highest, 2 electrons per orbital. We unpair degenerate electrons first before pairing them up, and so on. All those same rules that we learned for atomic orbitals apply here. So this is the correct diagram for C2, 2-. And then finally, to calculate the bond order, we have, it's 1/2, and then we take the number of bonding electrons, which are the number of electrons in bonding orbitals. Those are the ones that don't have stars next to them. So we have 2 electrons in this bonding orbital, 4, 6, 8. A total of 8 of the 10 electrons are in the bonding orbitals, sigma 2s, pi 2p, sigma 2p. So those 8 electrons are bonding, which means they strengthen the bond. And then we have only 2 of our electrons, these 2 here that are in sigma 2s, that are in anti-bonding orbitals, which would weaken the bond. So it's the difference between those multiplied by 1/2, and that comes out to a bond order of 3. So this would be predicted to be a triple bond order of 3, which is going to be choice A. Okay? Questions on MO theory? Yeah, in the back? The ones that are anti-bonding are the ones that have stars next to them. So for each orbital level you have, so for the 2s you have sigma 2s, sigma star 2s. The anti-bonding is the sigma star. Up here in the p part of the diagram you have these 3 are bonding, pi 2p, sigma 2p, and then these 3 which are empty in this molecule are going to be anti-bonding, pi star, sigma star. So anything that has the asterisk or the star next to it is considered anti-bonding. Anything else? All right, number 19. All right, we're moving on to some new stuff now related to mass and moles and things of that sort. So naturally occurring silver is composed of silver 107, which has a atomic mass of 106.905, and then silver 109. So these are the 2 isotopes that comprise silver in nature. If the atomic mass is 107.87, what is the percent abundance of the smaller isotope, 107 silver? All right, so for these types of problems where we're calculating atomic masses and relating them to isotopic abundances, there's only one equation we have to worry about. So remember that the reported atomic mass for any element, like the one we get off the periodic table, it's a weighted average of all of the individual isotope masses. So in this case we have 2 isotopes with different masses, and it's the weighted average of those 2 that's going to give us the number that we see on the periodic table. So we take the fraction of one isotope, which I guess I'll call, well, this one's 107. So the fraction of 107 silver times its mass plus the fraction of the second isotope, which in this case is 109, times its mass. So these fractions are the fractional abundances of each isotope, the relative amount that we have for each one. All right, so that's the equation. And for this one, we need to find the percent abundance of 107 silver, which is related to the fraction just multiplying by 100. So we have two unknowns in this equation. We're given the mass of each isotope. We're given the mass of each isotope, but we don't know the fraction of either one. So x and y would be our unknowns, those unknown fractions here. But remember that we always have a relationship between the fractional abundances, which is that the sum of the two, x plus y, has to equal 1. Or if there's more than 2, then the sum of all three of them would equal 1. So the fractional abundances total out to be 1 or 100%. So now we can write out the two equations. So the given atomic mass for silver is 107.87. That's equal to the fractional abundance of 107, which we're calling x, times its mass. The mass of 107 is 106.905. They're always a little bit different than the whole number. And then the mass for the second isotope is 108.905. And we call that abundance y. So that's our first equation. So we have two equations, two unknowns. We're solving for x, which is the abundance of 107. So if we rearrange this equation up here, y equals 1 minus x. We can make that substitution. So 107.87 is equal to 106.905 x plus 108.905 times 1 minus x. So this value, the second fraction here is just 1 minus the first one. And so we solve for x, which is the fractional abundance of the smaller isotope. Which comes out to 0.5175. And then the percent abundance is just that times 100. Although I guess in Blackboard you wouldn't enter in the unit, just the number. Okay, so that's what we come out. It's almost 50-50 for these two isotopes, a little bit in favor of 107 silver. All right, but like I said, for these types of problems, there's one equation. We could have, any of these terms be the unknown, but you just have to know how to use the equation and solve for whatever we're asking for. All right, any issues with that one? All right, number 20. Now we're starting to talk about conversions involving moles. All right, so we want to know how many phosphorus atoms are found in 5 grams of calcium phosphate. So one thing we'll need for this problem is the formula for calcium phosphate, because that's going to give us the molar mass of potassium phosphate, also tell us how many phosphorus atoms are in the formula, which are both important pieces of this. All right, so calcium phosphate, we have calcium 2 plus paired with PO4 3 minus. So we have to remember our polyatomics again. Phosphate is PO4 3 minus. So we cross over the charges. And so that means the formula for this compound is going to be calcium 3 and then PO4 taken twice. Okay, so that's the correct chemical formula for calcium phosphate. As part of this problem, we're going to need the molar mass. So as a quick review of how to calculate molar mass is the sum of the individual atomic masses. So this formula has 3 calciums. From the periodic table, remember these numbers below the symbols are the atomic masses. So calcium has a mass of 40.08. So each calcium is 40.08. So that's the contribution from calcium. We have 2 phosphoruses because PO4 taken twice means we have 2 phosphoruses total. And the atomic mass of phosphorus is 30.97 right there. Okay. So those are all in the periodic tables. You obviously don't have to remember all those. So that's phosphorus. And then finally for oxygen, we have 8 of them. Each phosphate has 4. There's 2 phosphates, so we have a total of 8 oxygens. Each oxygen is 16 grams per mole. So we get 310.18 grams per mole. So that's the molar mass of this compound, which we're going to use, because what we're looking for is the number of phosphorus atoms. And as we reviewed on Monday, there's a bunch of relationships involving moles, and if we want to find the number of atoms, we're going to have to use Avogadro's number, but we first need the moles of the substance to be able to use that. So we have to convert everything to moles first. So we're given 5 grams of calcium phosphate. We convert that to moles first by using the molar mass that we just calculated. So 1 mole has a mass of 310.18 grams. That's the number we just calculated, grams per mole. Alright, so that gives us moles of calcium phosphate. But then from here what we have to realize is we're trying to calculate the number of phosphorus atoms. So we have to think about how many moles of phosphorus are in calcium phosphate. Alright, so we want to convert to moles of phosphorus. We'll do this on another line for this one around our room. Alright, so you can think about that for a second. What do we do next? So the next thing we want to do is find out how many moles of phosphorus we have. Alright, so each formula unit of calcium phosphate has two phosphoruses in it, as we said. So there's going to be 2 moles of phosphorus for every mole of calcium phosphate that we have. So remember that these subscripts in the chemical formula tell you the relative ratios of each element in the compound. So there's going to be 2 moles of phosphorus per mole of calcium phosphate. So that's an important step that we can't forget. And now that we're in moles of phosphorus, we can use Avogadro's number to figure out how many phosphorus atoms that corresponds to. So there's 6.02 times 10 to the 23rd phosphorus atoms per 1 mole of phosphorus. All right, phosphorus is an atomic substance in this case. Alright, so that gives us 1.94 times 10 to the 22nd phosphorus atoms. The log of that answer, which is how we usually ask you for it on Blackboard because it's annoying to input exponents, is just 22.29. Okay? So mass to mole, which is a very common conversion we're going to have to do, and then we have to realize that there's 2 moles of phosphorus per mole of the compound before we use Avogadro's number. We could have also inverted things. We could have said that there's 6.02 times 10 to the 23rd formula units per mole, and then there's 2 phosphorus atoms per formula unit. We could have done these last 2 conversions in either order. It would have still given us the same answer, just conceptually a little bit different way of thinking about it, but they're both perfectly valid. Okay, questions on that one? Alright, number 21. We're getting a little bit low on time, so we need to motor here. I guess we have 3 more. Alright, a metal chloride with the formula MCl3 contains 35.62% chlorine by mass. What is the identity of N? Alright, so there are some problems like this in the final, which I don't know if we've gone through before, so let's figure out our approach for this. So if we ever ask you to identify an unknown substance, there's a couple different problems that'll come into play in. Usually what you're going to be looking for is the molar mass of that substance. That'll allow you then identify what it is, or at least narrow it down to one of the choices that's in the problem. So if we want to find the identity of the metal M, let's try to find its atomic mass. Okay? And to find atomic mass, or any molar mass, it's the number of grams per mole. So if we know how many grams of metal we have, and we know how many moles that corresponds to, dividing those 2 quantities is going to give us the atomic mass in grams per mole. So whenever you're trying to identify an unknown substance, think about molar mass, and then think about the fact that you'll need the mass and the moles. Now, neither of these quantities are given to us directly, okay? But if we have a mass percent here, let's assume that we have 100 grams of compound, because that's the most convenient thing to do whenever we're given percentages. So if we have 100 grams of compound, we have 35.62 grams of chlorine, and then the rest of that has to be whatever our metal is. So 100 minus 35.62 means we would have 64.38 grams of our metal. So if we're assuming 100 grams of compound, we can put that in for the mass of the metal, 64.38 grams. But now we need to figure out how many moles does that correspond to. And we're going to use the information for chlorine to help us determine that, and the chemical formula. So if we're looking for the moles of the metal, which is the denominator in that calculation, we don't know the identity of the metal. That's what we're trying to figure out. So we can't possibly convert this into a number of moles. There's just no way to do it because we don't know the atomic mass. But if we know the atomic mass of chlorine, we can convert that into moles. We have 35.62 grams of chlorine. The atomic mass of chlorine is 35.45 from the periodic table. That's a known element, so we can find its atomic mass from the periodic table. And then we also have a relationship between the moles of chlorine and the moles of the metal, because we know the formula is MCl3, which means that for every 3 moles of chlorine we have 1 mole of metal, or for every 1 mole of metal we have 3 moles of chlorine. So we can use that as a conversion, where we're going to put 3 on the bottom, 1 on the top, so we have moles of chlorine to cancel, and that converts the moles of chlorine that we have into the moles of the metal, which comes out to 0.3349 moles of metal. So we divide this 64.38 divided by 0.3349 moles, and so we get an atomic mass of 192.2 grams per mole, and now we can go to the periodic table and figure out which element is that has an atomic mass of 192.2. So we go to the periodic table, and if you've been paying attention in class this semester, this is not a surprising answer. That corresponds to the metal iridium, which happens to be my favorite. So 192.2 matches up with that metal there, IR. So we just find where, which of these numbers is closest to that, and that one's exactly 192.2. So the identity of the metal in this case is IR iridium. Okay? So when we have problems like this with an unknown element in the formula, you have to try to figure out the atomic mass of that element, and that'll allow you to identify it from the periodic table. Any questions on that? All right, next one here, number 22, talking about net ionic equations. Okay, so this one is, what we have to do here is think about what type of reaction this is. So we have sodium hydroxide, we have iron 2 chloride, both of them are ionic compounds. We have a base, but this is not an acid, so it's just going to be an ion exchange or precipitation type reaction. And then we can think about, the identity of the products. So we're taking sodium hydroxide, which is NaOH, iron 2 chloride. Iron 2 tells us that it's +2, so we have FeCl2, 2 chlorides to balance the charge. And then the two products of this, we're going to just swap the cations and the anions. Sodium pairs with chlorine to make sodium chloride, and then iron pairs with hydroxide to make FeOH2. We can put coefficients in quickly, so we have 2 chlorines, so we need 2 NaCl's, and then we also need to have 2 NaOH's to balance. So that's going to be the coefficients. They're usually pretty simple for these types of equations. And then finally we can figure out the solubility of these species. So we're starting with 2 soluble ionic compounds, in aqueous solutions, so we know the reactants are aqueous. But then the products here, we have to think about solubility rules. So sodium chloride, anything that has sodium in it is soluble, so we don't have to think about that one. It's just going to be soluble aqueous. But then iron hydroxide, most hydroxide compounds are insoluble except for the group 1A metals. There's a few other exceptions. But all transition metal hydroxides are insoluble. So FeOH2 is going to be insoluble. Take a moment to review solubility rules if that's something you've long since forgotten. So that's going to be the total equation here. But what we're looking for is the net ionic equation for this reaction. Now there's 2 different ways of writing net ionic equations. We could either take this, break it up into the total ionic equation, and then cancel out the spectator ions. Or another thing that we can do that maybe saves a little bit of time is realize that for a net ionic equation that involves a precipitation reaction where we're forming a solid, the net ionic equation is just the ions that compose that solid combining to make it. In other words, we have FeOH2 as the product. That's going to be in our net ionic equation because that's the insoluble species. And then the reactants for the net ionic equation are just going to be the 2 ions that make up your insoluble product. So iron hydroxide is composed of Fe2+, which starts as a soluble aqueous ion. It has 2 OH minuses in the formula, so then those are going to combine to make FeOH2. So this is kind of a nice shortcut way of writing net ionic equations. You find, for a precipitation reaction, find the 2 ions that are combining to make your precipitate and just write it out. The other long way to do it would be to first write the total ionic equation. So if we took this and wrote a total ionic equation, we would get 2 Na+, I'm going to write it small to fit it, 2 OH minuses, so that one separates into cations and anions. FeCl2 is a soluble ionic compound, so it separates into cations and anions. And then on the product side, we have 2 Na pluses still soluble, 2 Cl minuses still dissolved, and then finally our FeOH2, which is insoluble, we don't break up because it's a precipitate. So if we got to the total ionic equation, we would cancel out spectator ions, which are the ones that appear on both sides. So Na plus is on both sides, Cl minus is on both sides of the equation, and then again that leaves these two ions combining to make this compound. So you can kind of skip this intermediate step here in many cases if you want to go straight to here, but the real process that's involved is taking this equation, breaking up all the soluble species into ions, and then canceling out the ions that appear on both sides of the equation, which we call spectator ions. So if we're looking for which of the following species is in the net ionic equation, we don't have NaCl in the net ionic equation, that's going to be soluble. We don't have Na plus because that's a spectator ion, but we have 2 OH minuses as a reactant. We have FeOH2 as a product, so both of those are going to appear in the net ionic equation. Okay? All right, questions on this topic? All right, and then finally the last one for today, calculating molarity. So we have 3.58 grams of aluminum perchlorate dissolved in 125 milliliters of solution, and we want to know what is the molarity of perchlorate itself, okay? All right, so there's going to be a few steps here. We do need the chemical formula for this. I gave you the molar mass, but because we're talking about the concentration of one of the ions, we need to have that as well. So we have aluminum perchlorate is going to be Al3 plus combining with ClO4 minus. So we need to have 3 anions to balance the charge of the cation. So the correct formula for this is aluminum with 3 perchlorates. And what we're looking for in this problem is the molarity of the perchlorate anion, which means we need the moles of that. So remember that molarity is moles per liter. So we need the molarity of perchlorate, the moles of perchlorate divided by the liters of solution. All right, so again, we need both of these parameters to be able to calculate molarity. Usually in molarity problems, one of these is going to be given to us, and that's often the volume. So we see that our solution has a volume of 125 milliliters. We need that to be in liters to calculate molarity. So we just divide that by 1,000. So the volume of the solution is 0.125 liters. But now we have to do some conversions to calculate the moles of perchlorate that are in there. All right, so if we're looking for the moles of ClO4 minus, we have 3.58 grams of aluminum perchlorate. We're going to convert that to moles because we're eventually going to get into moles of one of the ions. We need to convert this to moles first. 1 mole of that compound. Sorry, AlClO3, only 1 aluminum. We put the molar mass in the bottom so that the grams cancel out, 325.32, which was given to us in this case. All right, and then we have to look for, again, what we're asking for, which is the moles of perchlorate. So we need to figure out how many moles of perchlorate are in 1 mole of aluminum perchlorate, and again, that comes from the chemical formula. There's a subscript of 3 after perchlorate, so that means we have 3 moles of ClO4 minus for every 1 mole of compound. And so when we work out the numbers, we get 0.033 moles of perchlorate. So we put that up here, and we end up with a concentration of 0.264 molar. All right, so molar, capital M, is moles per liter. So if we're going to calculate that, we need both of these quantities. All right, any last questions on that one? All right, that takes us to the end for today. We'll see you on Monday for the swan song of this class.